All right, today we're going to look at lesson 9.1, and it is the properties of radicals. Now, this is one of the longer lessons that we've had, so we are going to get through as much of it as we can, and then we're going to actually finish this tomorrow, okay? But before we look at the essential question, let's talk about what a radical is, okay? Is there anybody that can raise your hand and remind us what a radical is? Radical is another name for a square root, all right? So our essential question today says, how can you multiply and divide square roots? Well, before we can even get to that kind of stuff, we've got to know how to simplify radicals. Some of these are going to simplify easily in a calculator because they're going to be perfect squares or they're going to be perfect roots. But what happens when you stick a number into a calculator and you're looking at a decimal answer? Okay, well, you've got to know how to simplify a radical on paper. So let's just talk about radicals for a couple of minutes. First of all, the number underneath the square root sign or the radical sign is called the radicand. So when you hear me refer to the radicand, I'm talking about the number under the radical. A radical expression is any expression that contains a radical. So if you're looking at a problem that has a radical sign in it, it is a radical expression. Now, how do we tell if our radical is in simplest form? Because we're going to be asked over and over again today to simplify the expression. So how do we know if our problem is in its simplest form? Well, first of all, no radicand will have a perfect nth power. So basically, nothing under the radical will be a perfect square or a perfect cube. It will be simplified as much as it can be simplified. Okay? Nothing under the radical will contain a fraction. So the radical cannot have a fraction underneath it if it's in simplest form. And then lastly, no radicands will appear in the denominator of a fraction. So if your final answer is a fraction, there cannot be a radical in the denominator, all right? And we'll check some of these as we go. Now, how do we simplify a radical? How many of you have learned upside down division before? Just by a show of hands, how many of you have learned upside down division? Okay, all right? So for those of you that have not, it's going to be exactly like it sounds. In elementary, when you divided things, you had a division, a little problem, and you had a number underneath, and you divided, okay? We are doing upside down division. So we are going to take our number, and we're going to flip that upside down, okay? So it's literally what it sounds like. We're going to do upside down division. Now, here's the key to upside down division. You can only divide by prime numbers. Well, you got to know what a prime number is. Can somebody raise your hand and tell me what a prime number is? Daniel? Prime numbers are numbers that are only divisible by 1 and the number itself. So let's list some prime numbers. What is the very first prime number? 1 is neither prime nor composite. So 2 would be the first prime number. Now this is an excellent extra note to add. If you don't know what prime numbers are, write this list down. Okay? After the number 2, what would be the next prime number? 3. All right. What about after 3? 5. Good. We skipped 4 because 2 times 2 is 4, so it's not prime. What about what's after 5? 7. What's after 7? 11. Very good. 8 is not prime. 9 is not prime. 10 is not prime. So it's 11. And give me one more. 13. Now the reason I usually stop at 13 is because when we're doing upside down division, we're thinking pretty small numbers. We don't usually have to get any higher than 13. All right. But these are our prime numbers. So when we're doing upside down division, we're going to divide by only prime numbers. Now, we're going to continue dividing until we reach a prime number. So you're going to hear me after every time we divide, I'm going to say, is this prime? If it's not, we're going to keep going. But once we hit a prime number, we'll stop dividing, and then we will circle the pairs and make pairs just one of that number. So here's, if you've ever been to a wedding and the pastor said that these 2 people are getting married and they are becoming one, all right? These pairs of numbers are going to become one of the number, and then it's going to come out from underneath the radical. So step number 4 says you multiply all the numbers that you've pulled out together, and then leftovers go back underneath the radical. So let's look at example 1. We're going to simplify the expression. And I like to do my upside down division beside my problem. That way I can do all of my final answer work below the original problem. So we're going to do 24, and we're going to do upside down division. Now, what is a prime number that goes into 24?
7.
2 goes into 24, okay? Not 7, but there is another prime number that would also work. 3. So, does it matter if we start with 2 or 3? No. Okay, as long as we divide correctly, we're all going to end up with the same numbers at the end. So, we'll start with a 3. 24 divided by 3. Now, you've got a calculator. Feel free to use it. What is 24 divided by 3? 8. Okay, hopefully you don't need it for that, but you can use it. Is 8 a prime number? No, so I'm going to keep dividing. What prime number goes into 8? 2. 2 goes into 8? 4. Is 4 prime? No. Then we're going to keep going. What goes into 4?
2.
How many times? 2. Now, is 2 a prime number? Yes. Now, notice what I do not put. If I reach a prime number, I'm not putting my division symbol. And here's why. When I go to look for pairs, I'm supposed to be looking at all the numbers along the outside. If I put this division bar there, I might forget that 2 is part of the numbers that I should be looking at. So once you reach a prime number, leave the division bar off. Okay? Now, we're looking for pairs. So do we have any pairs in letter A? Yes, we have a pair of 2s, and that pair of 2s becomes just 1, 2. Okay? Now, for those of you that are like, why? I don't understand. I need to visually see why the pair becomes 1. All right? Imagine that I took those prime numbers and I put them back under the radical. So 2 times 2 is 4, times 2 is 8, times 3 is the 24. I've broken down the 24 into prime numbers. Okay? What is 2 times 2?
4.
And what is the square root of 4? So that is why the pair becomes 1. Because if it was under the radical, it would make a 4, and the square root of 4 is just 2. All right? So we've got that 2. It's the only pair we have. So it's the only number coming out from under the radical. And what are my leftovers? What numbers are left over?
2.
And what do you think I'm going to do with 2 and 3 before I put it back underneath?
Multiply.
What is 2 times 3?
6.
So the simplified answer is 2 times the square root of 6. Now, you can try it on your calculator. You can do the square root of 24 on your calculator, and it's going to give you a decimal answer. We're not looking for decimal answers, okay? We're looking for simplified radical answers. So 2 times the square root of 6. Now, let's look at letter B. Am I going to do anything with the negative that is outside the radical right here at the beginning? No, so I'm going to go ahead and bring it down because it is going to be part of my answer, but it has nothing to do with my upside down division. So I'm going to take 80, and I'm going to do upside down division. What goes into 80? 5. And what else? 2. So here's what I want. This group right here, I want you guys to start with a 5. Okay? The rest of you, I want you to start with a 2. And let's see if we don't come out with the same numbers, no matter if we start with a 2 or a 5. All right? On the board, I'm going to put the 5. 80 divided by 5. Now listen, if you don't have a calculator, I don't have a calculator up here right now, but I can still do this math. 5 goes into 8 one time with 3 left over. My remainder goes beside the next digit. Now 5 goes into 30 6 times. So you can do upside down division without a calculator. But I know that 16 is not prime, so I'm going to keep going. What prime number goes into 16? 2. How many times? 8. I know that 8 is not prime. What prime number goes into 8? How many times?
4.
What prime number goes into 4?
2.
How many times? 2. So again, I've reached a prime number, I'm done dividing, and I'm not going to put that division symbol down because I don't want to forget about that 2. Okay? Now, I'm looking for pairs.
3 2s.
How many pairs do I have?
2 pairs.
I have 2 pairs of 2. So this pair of 2s becomes a 2. This pair of 2s becomes a 2. Now, I've pulled 2 numbers out from underneath the radical. Carson, what am I supposed to do with those 2 numbers? According to the steps that we have in our notes, what am I supposed to do with all the numbers that I pull out from under the radical? So, we are going to show this in our notes, okay? 2 times 2. Because I want you to know when you look back exactly what you did. You took those 2 2s and you're going to multiply them together. And then we can put our radical, because what is left over that has to go back underneath?
5.
A 5. Now let me ask you this. Those of you that started with 5, you were with me, right? So we had 3 2s. We had 4 2s and a 5. This side of the room, you started with a 2. Did you still end up with 4 2s and a 5 by the end? Yes. Okay, if you didn't, then you did something wrong. Because no matter what prime number you start with, as long as it works, you should end up by the end with all the same digits. All right, now, what is negative 2 times 2? Negative 4. Bring down the square root of 5, and there is your simplified answer. All right? All right, we're going to focus on the 75 to begin with. So we know that the square root of 75 is not a perfect square. So what prime number goes into 75? 5. Okay, 5 goes into 7 once with 2 left over. 5 goes into 25 5 times. What prime number goes into 15? 5 or 3, doesn't really matter, but 5 goes into 15 3 times. Is 3 prime? So I'm done dividing and I'm looking for pairs. Do I have any pairs?
1 pair.
I have a pair of 5s. And that pair is going to become just 1 5. And it's going to go on the outside of my radical. Now, I'm going to leave a little bit of space before I draw the radical because I also have a variable in this problem. Okay, but before we look at the variable, what number needs to go back under the radical?
3.
My leftover 3 needs to go back underneath the radical. How many of you got that far on your problem? Okay, awesome. Now, into the 5th, all right? Let's go back. We got to go back for just a minute. When we are looking at a square root, right here on this little ledge, there is nothing. But we know that when there's nothing on that ledge, it is an understood what?
1.
No.
2.
It's the square root of something. So something that has been squared has an exponent of 2. So let me ask that question again. When there's nothing on the ledge on a radical sign, what is understood to be there?
2.
A 2. Okay? That's why we've been looking for pairs of numbers. All right? But that's also important because this is what we're going to deal with when we're trying to simplify variables. Okay? The root of 2 goes into the exponent of 5 how many times without going over? 2 goes in, the root of 2 goes into the exponent of 5 how many times without going over?
2.
Twice, right? So guess what? 2 n's are coming out from under the radical, which we're going to write as n squared. Now, there is a remainder though, because 2 times 2 is only what? 4. And there were 5 n's underneath to begin with. So, how many n's are left over?
1.
That means there's 1 n still under the radical. And my final answer is 5n squared times the square root of 3n. Now again, for those of you that are visual, let me show you what this is. N to the 5th is the same as n times n times n times n times n. Correct? I got a pair of n's, I got a pair of n's. This pair becomes 1 n that comes out. This pair becomes another n that comes out. So, how many n's come out from underneath the radical? 2. And how many are left under the radical? 1. So for those of you that need to see it drawn out, this is what you need to put in your notes because this is what we just did. Okay? The shortcut says the root goes into the exponent how many times without going over? Anything remaining or left over stays underneath. Okay? Are there any questions? Because this is probably the trickiest thing we've done so far. All right, let's continue. This time, when you're looking at letter C, what is underneath the radical? A fraction. So the very first thing we're going to do, we've got that little negative sign outside of the radical, so we're going to do what with that negative sign? Bring it down. Awesome. Now, the first thing you're going to do when you see a fraction underneath your radical is we're going to split the fraction apart. So we're going to write the square root of 17 over the square root of 100. This is going to allow us to see a little bit more clearly if we have a perfect square or what we need to simplify. So if you're looking at this problem, are either of these perfect squares?
No. Wait, no.
Okay, the square root of 100 is what? 10. So without even picking up our calculators, I can go ahead, I'm going to bring down the negative, I'm going to bring down the fraction bar, and I'm going to put a 10 in my denominator. The square root of 100 is 10. Now, 17, is that a perfect square? No, so we are going to have to try and simplify 17. But what do you notice about 17? What kind of number is it? It's a prime number. So is it even going to simplify? No. So we're just going to bring down the square root of 17. Now, we're boxing this in, but let's check. Remember at the very beginning we talked about how to tell if a radical was simplified. Okay? Let's go over those things. Number one, is there a perfect square underneath a radical? So 17, is it a perfect square?
Yeah. No.
No, we already decided that. It's not a perfect square. It cannot be simplified. So we're good. Is there a fraction underneath the radical?
Yes.
No, what's under the radical?
Oh, 17.
17. We took care. It started with a fraction under the radical, but by splitting it up and simplifying the square root of 100, we already took care of that. So there's no fraction under the radical. And the last thing said there would be no radical in the denominator of a fraction. So our answer is a fraction. Is there a radical in the denominator?
No.
No. Okay? Anybody else agree with Travis? He's the only one answering me right now. Is there a radical in the denominator of our answer?
No.
No, there is not. There is a radical in the numerator, but that's okay. There just can't be a radical down in the denominator, and there's not. So this is our final answer. All right, let's move on to letter E. It's a fraction. So what's the first thing we're going to do when we see a fraction under the radical sign? Split it up. So we got the square root of 36 over the square root of z squared. What is the square root of 36? 6. And what's the square root of z squared? Z. That's my final answer. Look at letter F. What's the first thing we're going to do with letter F? Split it up. 4x squared divided by the square root of 64. What is the square root, Malcolm, of 4x squared? 2x. The square root of 4 is 2, and the square root of x squared is x. And Kayla, what's the square root of 64?
8.
8. Now, before we box this in, we have a fraction in our answer. What do we always have to do with fractions? Simplify. So we're looking at the 2/8. Will that simplify? Yes, to what? 1/4. So x over 4 is your final answer. Now, you can put the 1 in front of the x if you want. You can leave it off. It doesn't matter. It's the same thing either way. But we've got to make sure you simplify your fractions. Now we move on to example 1 continued. We move on to letter G, and you notice there's a new note for you. So first thing I want you to do is I want you to highlight it, but then let's talk about why this new note is there. It says use upside down division, so that hasn't changed, but circle sets of 3 instead of pairs. Why am I now going to be circling 3s instead of pairs? Anybody have a thought? If you look at the original problems in this next section. Avery.
You're using bigger numbers.
Okay, no, that's a good thought. Loza? Say it again. Okay, a 3 under the radical? Yeah, what's that called right here? What's this little 3 called? The what of the problem?
No.
Starts with an R. The root, right? The root tells me how many numbers I need to look for and circle. Okay, now does that make sense?
Yes.
If we go back to the first 6 problems we did, they were square roots, right? That's 2. So we circled pairs. Now the root is a 3, so instead of pairs, we've got to look for sets of 3. Okay? What if the root was 5? We need sets of what? 5. Okay? So the root tells me how many of a number I'm looking for. Okay? How many sets or if it's a pair. All right? So these are cubed root problems. So nothing else changes. We're still going to be doing upside down division. So let's do upside down division with 54. What goes into 54? 3. What else goes into 54? 2. So you can start with either one. I'm going to start with 3. Again, 3 goes into 5 once with 2 left over. 3 goes into 24 8 times. Is 18 prime? Nope. So I'm going to keep going. What prime number goes into 18? 3. All right. Or 2. Okay, 3 or 2, doesn't matter. 18 divided by 3 is 6. What prime number goes into 6?
2.
Or 3, doesn't matter. 2 goes into 6, how many times? 3 times. All right? Now, I've reached a prime number. I'm done dividing, but I've got to be careful. Because instead of pairs, I'm looking for sets of 3. Is there, Tristan, a set of 3 in this answer or in this problem? Nobody said they had to be beside each other. Yes. Okay. Nowhere along the way did I say they have to be in a row. Okay. You're looking at all the numbers along the outside of this problem. There are 2 3s right here, and there is a 3 right here. So absolutely there is a set of 3, and that set of 3 becomes just 1 3. Okay. So nothing has changed. It's just we have to find sets of 3 instead of pairs. So the 3 comes out from underneath the radical. We put the radical with the root on it, okay? Make sure that little ledge is very distinct and very obvious because we don't want it to look like you tell me 3 to the 3rd is out there. But 3 times the cubed root of, what's the leftover number that has to go back under the radical? 2, all right? Now, I keep reading these as 3 times the square root of, or 3 times the cubed root of 2. Why am I saying times? What lets me know that this is a multiplication problem?
Because it's like to the 3rd up top.
Somebody raise your hand and tell me, how do I know this is multiplication? There is no sign between a number and a radical. It's multiplication. All right? So look at letter H. We have a fraction underneath the radical. So what is the first thing that we're going to do in letter H? We're going to split it up. But remember, it's the cubed root of A over the cubed root of negative 27. Now, here's something brand new we haven't seen before. There's a negative under the radical. And normally I would say can't do it. Okay? That's imaginary numbers. That's a whole nother lesson that you're going to learn probably not till algebra 2. Okay? But here's why this works here. The root is odd. As long as your root is an odd number, you can have a negative under the radical. So grab your calculators. You're going to do the cubed root of negative 27. So look at your button, your square root button. Above it, it says cubed root, right? So you hit shift, hit your square root button, and then punch in negative 27 and tell me what it gives you for the cubed root of negative 27.
Negative 3.
Because negative 3 times negative 3 is positive 9, right? What's positive 9 times negative 3? Negative 27. So my denominator is negative 3. That's a perfect cubed root. So I don't even have a radical left in the denominator. All right, what about the cubed root of A? Can I do anything to simplify the cubed root of A? No. Okay? Because this is just A to the first, and we know 3 does not go into 1 evenly. So I'm keeping the cubed root of A as my numerator. Is that okay? Can there be a radical in the numerator? Yes. So this is my final answer. Okay? Now, you could put that negative sign out in front of the entire answer, or you can keep it with the 3. It does not matter to me. Either way, it's going to be the right answer. All right? Now, take a minute with your partner and work letter I. All right, let's talk about letter I. It's a fraction underneath the radical, so what's the first thing we have to do? Split it up. So we have the cubed root of 25c to the 7th, d to the 3rd, divided by the cubed root of 64. Now remember, we're always trying to see if it's a perfect square root or a perfect cubed root. Before we spend our time with upside down division, see if it's a perfect cubed root. So what about 25? Is 25 a perfect cubed root? No, it's not. It's a perfect square root, but it is not a perfect cube root. So we're keeping the cubed root of 25. We're keeping 25 under the radical. But what about c to the 7th? Okay? 3 goes into 7 how many times without going over? Twice. So how many c's are going to come out? 2. All right? But if I'm looking at that, 3 times 2 is only 6, which means I had how many c's left under the radical?
1.
Okay? So there's 1 c left underneath. All right? Layla, what about the d? The root of 3 goes into the exponent of 3 how many times? Once. So how many d's are coming out? Are there any d's left over? There are not. Over. Now, did you stick this in your calculator? What is the cubed root of 64?
4.
It is 4, because 4 times 4 times 4 is 64. And there is your final answer. Now remember, you've got a fraction. You've got c squared d over 4. All right? That doesn't simplify those, so I can move on. All right? Another way that you would see this answer written is c squared d over 4. And then they would drop the cubed root of 25c off to the side. Okay? Now I'm okay with you leaving it like this right here. But just understand, anything that's not under the radical is part of a fraction that could possibly be simplified. But we're okay here because c squared times d over 4 is not going to reduce at all. All right, now moving on to example number 2. It says simplify the equations. Does anybody see a mistake in the directions right here? Are these equations? No, they are not. So I want you to cross out equations on your notes, and I want you to put expressions. Okay, these are still expressions. They are not equations. That is my bad. All right, but notice underneath I've given you the steps to simplifying these expressions. We're supposed to simplify the radicands if possible. Then we're going to add the coefficients of the terms with the same radical. Now, let's review what a term is. Because if you don't know what a term is, then you're not going to know how to combine like terms. Can anybody raise your hand and remind us all of what a term is? Terms are the parts of an expression being added together. So she's exactly correct when she says that the square root of 6, which actually it's the negative square root of 6, that is a term. All right, what's another term then in this problem? Anybody? 3 times the square root of 2. Listen, half the battle in math is being able to read the problem that you're working. This is not 3 to the square root of 2. This is 3, what did we talk about earlier? Times the square root of 2. So 3 times the square root of 2 is absolutely a term, which leaves us with what as our last term in this problem? 10 times the square root of 2. Now, we are essentially going to combine our like terms. But before we can do that, we have to simplify these radicands if we can. We have to look at those numbers under the radical and ask, can they be simplified? So, looking at letter A, we have the square root of 2. Can we simplify the square root of 2? No. 2 is a prime number. It cannot be simplified. What about the square root of 6?
Yes.
All right, we think yes, but what goes into 6? 3 how many times? Do we have any pairs? Because we're done. 3 times 2, we have no pairs. So 6 actually cannot be simplified either. And of course, we already answered the question that the square root of 2 cannot be simplified. So everything's in its simplest form. The next question is, do we have any like terms? So Jamara, looking at letter A, do we have any like terms? Now look what we put in the notes. Add the coefficients of the terms with the same radical. What makes them like terms? They're going to have the same exact radical piece. So do we have like terms? What are they? Give me the whole term. Not 2 to the square root of 2. 3. 3. There's no sign between the 3 and the radical. So what operation is that? Times. So read it again. 3 times the square root of 2. And 10 times the square root of 2. Awesome. Now, imagine this was a 3x and a 10x. How would we combine those like terms, Jamara? What would we get? No, you just multiplied them together. Remember when we combine like terms, we add them together. So what would we get? No x squared, just x, okay? Remember back when we learned to combine like terms, we add the coefficients, we left the variable part alone. So the same is true here. We're going to add the coefficients, which obviously are 3 and 10, and that gives us 13. We're going to leave the radical piece alone. It's still going to be the square root of 2. So 13 times the square root of 2, bring down the minus the square root of 6, and then we ask ourselves, are there any more like terms? No, this is a square root of 2 and a square root of 6. They do not have the same radical part, so they are not like terms. So our final answer is 13 times the square root of 2 minus the square root of 6. Let's look at letter B. 4 times the square root of 7. Can we simplify the square root of 7? No. So we're going to bring down 4 times the square root of 7 minus 6. Can we simplify the square root of 63? Possibly. It's a bigger number, so there's a very good possibility. So we're going to do upside down division. What prime number goes into 63?
7.
How many times?
9.
9. What prime number goes into 9?
3.
How many times?
3.
Now, here's the question. Are we looking for pairs? Are we looking for sets of 3? Luke, based off of the square root of 63 that we're simplifying, should we be looking for pairs or should we be looking for sets of 3, sets of 4? All right, why? What tells us how many numbers have to be in our sets? Remember, we talked about this a second ago. Does anybody remember? What tells us how many numbers have to be in our set? Layla? The root. So Luke, looking at the square root of 63, right? There's no number right here, which makes it an understood what? An understood 2. So we should be looking for if there's an understood 2 right here, we should be looking for pairs or sets of 3. Pairs, because that's a root of 2. Okay, do we have any pairs? All right, we got a pair of 3s, which is going to become just 1 3. Now, here's something new again. So are you paying attention? We have a 3 that we're going to pull out, but there's already a 6 outside of this radical. So what do you think we're going to do with the 6 that's already there and the 3 that we're pulling out? Multiply. Very good. So for our notes, put every single step down. So show yourself that you are now going to multiply the 6 that was already there by 3. And then, of course, what's left underneath the radical? What's left over? 7. All right, so 4 times the square root of 7 minus, what is 6 times 3? 18 times the square root of 7. And are these, Chase, like terms that we can combine?
Yes.
So how do we combine them? Are you going to add them, though? You're going to subtract because it's 4 minus 18. So what is our final answer?
14 times square root of 7.
All right. Anyone disagree with his answer?
Negative.
It's negative, right? 4 minus 18. 18 is bigger, so we have to take the sign of the bigger number. But again, we combine the coefficients, and the radical part of the problem stays the same. All right. Now, this is where we are going to stop for today.